And we should be live. If anyone in the chat wants to say hello, that's always great. We're going to wait a minute or two before we really get started. I know we're a minute early. Let me just get situated here. And I think I saw someone comment on Meetup trying to get in. How's everyone doing? Cool. I see some people here already. Again, if you want to say hello in the chat, it makes it more fun for me, but also hopefully for you, kind of seeing who is watching. And if you want to share where you're watching from, that's always awesome. And maybe even a little bit about why you're interested in computer vision or machine learning. Maybe a little bit about what you've done before, if you've done something with it before. I'm streaming from Seattle. So I don't know if anyone else is in the area or if you're from all around the world. We get people from everywhere, which is really cool to see. So it said from Key West. Nice. Welcome. Welcome. Someone said from Pompeii, UK. Welcome. Yeah, it's always fun to see what time is it over there. It's like a 14-hour difference or something, right? And again, we'll get started here shortly. Just gonna wait, make sure people can roll in at the beginning. We'll get going. We're gonna do some slides, and then we'll go into some hands-on code. Actually, while people are rolling in, let me share some links in the chat. By the way, all the links to follow along are in the description as well. So if you're watching this recording or you just weren't able to follow along at this moment, you can find these in the description, but I will also share them in the chat right here. The main thing is, if you want to follow along, something you probably don't already have, perhaps, is a Union serverless account. It's going to be the MLOps pipeline platform that we're going to be training our model in today. We'll talk more about that soon. It could take 3 to 5 minutes to process it, so it's good to try to sign up now. And then if it doesn't let you through, let me know. So if after like 5 or 6 minutes you don't get an onboard email, let me know. It might be something I have to push you through. Like if you have a new GitHub account, it might be flagged. And it's free to sign up. There's no card or anything required, and you get $30 of cloud credit in there. And the other thing, again, if you want to follow along for every part, this is slightly optional here, is have a Hugging Face account. I'm going to show moving a model from our pipeline platform over to Hugging Face, which is like a model store. And then we'll show how to kind of bring that model down and run your model locally, because we're actually going to train a pretty efficient computer vision model that you can run on your local computer. Most computers can probably handle it, even if it's a slightly slower frame rate. But you can actually even deploy it on a Raspberry Pi, which I've done. You'll get a slower frame rate on Raspberry Pi, but I'll kind of show how to train this model, how to build a reproducible pipeline, and then how to bring this model kind of back into your local device or on an edge device. And then here's the GitHub page, which uses the code or has the code that we're going to use. And you'll want to go ahead, like when we're following along, again, I'm going to go through some slides. But if you want to go ahead and start poking around, you'll actually see there's an open and collab button. And that's the environment I recommend running in for this workshop. So you don't actually have to do any local environment setup. Should be a pretty smooth process to run everything. And then last is, here's a link to a Slack group. Ask the questions during the workshop in the live chat on YouTube or LinkedIn, where we're streaming. I will see them here. But if you have questions after the workshop, the Slack channel is a good place to join. So for anything we talked about, or if you want to just discuss ML and MLOps and maybe do a more permanent introduction there, that's a good place to do that as well. And I see other people commenting. Someone else is from the UK and they said it's 8 p.m. Awesome. That's not as late as I thought. I guess you're the next day ahead, I believe, right? Yeah. And then someone said they're from Canada. Awesome. Welcome, welcome. And again, okay, I think we'll get going here. Again, for anyone joining, we're going to go through some slides just to kind of set up some of the concepts and make sure everyone's on the same page. And then we're going to go do the hands-on part where you actually come away with a computer vision model like you see running here on the screen. And I'll talk about how to create your own data set for this as well. So hopefully my goal is like, we're going to all build the same model during this workshop in about the hour or less. And then you'll have the knowledge to collect your own data set, build another pipeline, and bring your model down on your computer or on a Raspberry Pi, and you'll kind of have all the knowledge equipped where you can go do this on your own data set. So I'm going to go ahead and share my screen here in presentation mode. So again, for the clump of people I just saw join in, I shared links in the chat, but they should also be in the description as well. So if you want to follow along, you can go ahead and hit that sign up for these 2 accounts and then start looking at the code if you want. I know I like to poke around a little ahead of the talk sometimes. So we're going to build an object detection model, kind of like here you see on the left. This is on some stickers, but this model could be trained on kind of anything. And we'll talk more about what object detection is in a minute, but you might already be familiar with it, or you might see, we're detecting objects in an image, but we're not just doing classification. We're actually localizing where they are within that frame and drawing a box around it. And then to do this, we're actually going to also build a pipeline. So we're not just going to train a model on our local computer, like in a notebook. We're actually going to kick off kind of a production level pipeline and workflow here. And so this is what a workflow looks like. It might be a little small on your screen potentially here. Again, we'll go ahead and build this though. So don't worry, we're going to talk about how to download a data set. We're going to download a model or initialize a model from PyTorch. And then we're going to train that model. We'll also verify the data and annotations are correct. And then we're going to evaluate the model. And then we'll upload that model to Hugging Face, which is one of the features they have is like a hub to store models in. And then we'll talk about how to pull that model back down to your local device. And like I mentioned, this could be like a model you deploy on a Raspberry Pi or an edge device or have running on your computer. Just a tiny bit about me. My name is Sage Elliott. I work at Union. You can find us at union.ai. You're going to see a demo of Union today, but it's we're going to use it for the pipeline part. It's a platform for building AI workflows and also deploying models. We're going to see the kind of training use case today. And then I live in Seattle. I also run an AI book club. If we're connected on LinkedIn, you might have seen it before. We had a ton of people show up the other day. We just read Building Large Language Models from Scratch. And in January, we're reading putting LLMs in production, I think is what it was called. So if you're interested in learning more about AI concepts, the book club's a fun thing to join. And previously, I've actually done a lot of work in computer vision and ML monitoring and the MLOps space, and also a background with hardware, IoT, and robotics. So I really like tying all those things together when I can. So you might mention me talk about putting like the model on a Raspberry Pi several times, because I think it's a really fun project. Has anyone ever put a machine learning model on like an edge device? Because it's a little bit different than deploying a model in the cloud if you've done that before. It's harder to monitor data sometimes. So like I've actually done this, like putting edge devices in fields, like for farmers where you don't have a consistent connection. So there's all these different things that you have to think about sometimes, which is interesting. If you want to stay connected, you can find me on LinkedIn. But I also shared that Slack channel earlier too. I'm in there. So you can connect and ask questions there as well. And then I saw more people join. So I know some people already said hello in the chat. Feel free to say hello again. And again, put in the chat, where are you watching from? What are you working on? And maybe why you're interested in computer vision pipelines. Do you already have a fun project in mind? Let me know. Someone said they are running Llama 3.2, 1 or 3 billion parameter on a Raspberry Pi 5. And it actually works. That's awesome. I actually haven't tried putting a larger Llama model on a Pi yet. But I'm glad to know it works on a Pi 5. I actually have a couple of those laying around right now, 8 gigabytes as well, so they should work. I also recently got, there's an AI hat that is new, and I haven't played with it yet, but it is an AI accelerator that you can add onto your Pi. And then I think you can run at something like 26 TOPS, which is tera operations per second, I believe. So I want to mess around with that too. That might help. I'm curious with the Llama 2 if it's like laggy or if you had any issues with it or if it's just super smooth. That's really cool. All right. And then a quick overview again for today's workshop. We're actually going to create a whole workflow to train our model that includes creating a container image for reproducibility. We're going to download a data set, download model weights, process and visualize that data, fine tune an object detection model, evaluate the model, save the model to Hugging Face Hub, and then use that model to not predict sentiment. I think this from, I didn't update this, to actually do object detection. All right, so what is object detection? So again, kind of like the image you saw before, it does classification and localization. So you might be familiar with classification. It's often kind of an earlier project that people work with machine learning, where maybe you feed an image of a cat or a dog and to a neural network, and you say, is there a cat or a dog in this image? And it just says yes or no. But it doesn't say how many there are. It doesn't tell you where they are in the image. And if you have both of them in there, it can kind of confuse the classification model sometimes. So object detection, you can have multiple different classes of objects in the same frame predicted. You can have a count of how many there are. And then you also get this localization, which is where they're drawing a box around where that object is, which opens up a lot more use cases for computer vision. Like now you can do counting. Like you could say, oh, there's 4 of these stickers in there, and there's 3 of the other type. You could do tracking. So where are objects going? You could count them as they cross a line. And then you can understand the localization, like where they are, and even interaction sometimes, like is this object interacting with another object? And today we're going to be using a model called Fast RCNN or Faster RCNN. You can read the original paper there, but don't worry about it. We're not going to go too in depth in this workshop. And PyTorch makes it really easy to basically import this model, give it data, and then it can learn from that data set. And we'll have our own object detection model running after this. And again, I hope that you'll learn the skills to bring in your own data and maybe build a cool project on your own. So quick thing about annotation for object detection, and I can go deeper into this after we run the code. So if you want to ask me questions about annotation later, let me know. But you're going to want to build your own data set. So again, for today, you don't have to do this because I'm going to give you your own data set or a data set that I built. But things to think about when you're curating it is the amount of data, the variations of that data, proper labels, unlabeled objects, and then usually split this into a train, validation, and test data set. Some annotation options, Label Studio. This is what I use. It's open source, really easy. They also have a managed version called Human Signal that I think has a lot more features. CVAT, Label Box. There's a whole bunch, again, that you could look into. Some of them have really smart features now, too, to help you label faster. I will just show real quick. I'll share the link to Label Studio first. And then I'll just show real quick. And again, I can go more into this later if you want, but this is kind of what labeling looks like in Label Studio here. I have a project that I already set up with 2 different labels. And let's say I delete this one and I want to relabel this. I'm basically going to draw a square around that object. And I want it to be as precise as possible. So for example, if I had a whole bunch of labels and they were really all over the place like this and not really tight around the object, it's going to cause issues with my model. Same if I had this label and it was just, labeling part of it, it's also going to confuse the model. So you want to be as tight as possible around the edges of it. And it's okay if it overlaps with another object. In that square, it's going to be looking in there and actually do a pretty good job of determining what belongs to that object. And we'll see today, we're actually not even going to have a huge data set, and it's going to learn pretty good. And then you can add more data and make it better. So some people ask, what's the minimum amount you need? It really just depends on your project. And you'd be surprised sometimes, you might have 100 images and your model might kind of start performing pretty well, and then you can keep adding data to it. Has anyone done data annotation before, or for making your own computer vision model? There's different types too. We were just showing the squares today for object detection, but you have instant segmentation, which is where you're really tracing around the object, and then it's a more precise localization of where the object is inside the frame. And then just a quick note on MLOps and building kind of ML pipelines. It's the set of best practices and tools that aim to deploy, monitor, and maintain your ML model or computer vision model in production. And then I always like to kind of think of it as doing it reliably and efficiently when you're building out pipelines. And this is a super simplified pipeline here. You probably have way more than this, but typically for every pipeline, you're going to have these steps in some manner. You're going to be collecting data. In our case, we're also annotating that data. And then you're going to train a model, evaluate that model, usually ship that model somewhere in production. Again, this really varies, like we talked about putting on edge devices today, but this could be in the cloud. And then once that model's out, you usually want to monitor it in some fashion. This could be connecting to some platforms that make this really easy, looking for things like data drift when the data coming into your model changes quite a bit from the training data set. That's a good indicator that your model might not be working as well on it. And then you also want to monitor your outputs from your model and see if any variations going on there. And then typically you're going to be probably collecting data in production and then kind of build a loop in this, often called like the data flywheel, ML flywheel, ML lifecycle. You can use that new data and kind of do all these steps again. So it's really common that you build out a workflow that you can rerun efficiently and reliably to kind of keep putting models in production and improving it. And again, there's a lot more steps that you might often have, like the processing the data. If you're doing LLMs as well, you have like prompt management, maybe vector databases, guardrails, and then A/B testing for all sorts of different ML applications. So there's a lot of tools that make this easier to do, all these different steps. And we need compute for them to run on, though. And you usually need that compute to like scale up. Every time you run a workflow, you also probably want a version of it, kind of thinking about how you version your code. You want versions and snapshots of workflows, especially if you're doing a lot of experimentation, or in some industries, you might even need more validation, where you actually can go back and trace like what data was used on a model. Like that's a common thing in some healthcare and fintech applications. So again, yeah, you want to think about scalability, reproducibility, versioning, improved efficiency, and cost efficiency as well. And a couple of things that I've seen make a big impact, especially when you're thinking about like cost efficiency and improved efficiency actually for people, for developers as well, is utilizing local and using a pipeline that's optimized for local development, not just cloud. And so you should be able to utilize like your local computer to write a pipeline and then kick off a production job in the cloud. Leverage caching in the pipeline. So this is a little example of like rerunning a whole workflow that's training the model. But maybe we don't want to download the data set and process the data every single time we want to change a hyperparameter. So we can rerun this and then just use cache versions of data. So it's not re-downloading the data every single time. And then we have task level resource management and containerization. So when we have all these different tasks in our workflows, sometimes you need a GPU maybe, sometimes you don't. And GPUs are really expensive, and you might not have that many of them in your like development cluster. So you only want to use it when you need it. Then that would be like often in training cases or evaluation for deep learning models. So for example, the downloading data set here probably doesn't need a GPU. So you could just declare, I want 2 CPUs and like 4 gigabytes of memory for that task. And then for my deep learning task, I actually do want GPUs, and you're only using them when you need it. And then also some of you might be familiar with like type safety. This helps kind of reduce your debugging time. Usually like, you know, your platform or code can yell at you when you're trying to output something that shouldn't work with your task. And so again, we'll see this in action here in a minute. So today, to kind of build all that out, you'll actually see to kind of get all that, all the features we talked about, like versioning, reproducibility, container images, caching. It's really just a few lines of code that we're going to add above a Python task in a decorator. And so we'll see this in action here in a minute as we get into the code. So these decorators and like just a few lines of code are really doing a lot of heavy lifting of adding all these really common best practices that are usually needed in ML pipelines. So today we're going to be using Union, specifically Union Serverless, which is in beta. Again, I shared the link earlier. I'll share it again, but you should be able to sign up. And then that'll make it really easy for us to run our code without having to set up like a Kubernetes cluster. It's also built on a open source project called Flyte. You can check this out on GitHub as well. So I think actually most of the stuff we're going to see today, you could actually replicate in the open source. Union does have some other features like artifact management, role-based access, and stuff built in. And then as declarative infrastructure, this is where we're going to declare our infrastructure right in our code. So it really empowers AI engineers or ML engineers or data engineers, whoever's using this orchestration tool, to have access to the compute infrastructure, and they don't really have to go through people or set up tickets to get models out of production or do experimentation faster. Then it has the other things we talked about, like versioning, caching, type safety. It's really flexible, like all those libraries we saw. It has a really robust plugin ecosystem, but also out of the box, a lot of Python libraries should just work with it. And it's scalable. It's built on top of Kubernetes, and it has a nice user interface and Python API that we'll see in action here. For saving and versioning the model. So like I mentioned, it's version in Union, but we'll also show how to move a model out into Hugging Face and then pull that model down into a local environment. So I hope everyone's ready for the code portion. I'll share the link again in the chat here. You should be able to open this up and you'll get, you'll get something like this. And then you'll just want to hit this Open in Colab button. Open in Colab. This will open up a notebook hosted in a Google Cloud environment. So I guess you might need a Google account to be logged in here, but not a Google Cloud account or anything. This just kind of runs as a layer on kind of like Google Drive, but it's going to give you a whole environment to run in. And then what I like to do when I'm following along with a workshop is hit Save a Copy in Drive. This way, this will be your very own copy of this notebook, and you can actually make code changes and text changes, and they'll stay permanent here for you. Don't worry about breaking it. You can always come back to this original one. So you can bookmark this or the repo and come back to it if you accidentally do break anything. So once you're here, you can hit this first code cell. We can run this first code cell. You can run it by hitting the play button, or when it's highlighted, you can hit Shift Enter. I often hit Shift Enter, so you might not see me clicking the play button. This is going to install some common libraries. We're going to use Union. We're going to use PyTorch, Torch Vision, and some other tools for our data set. So this should take a minute to install. While this is installing, if you haven't already, you can sign up for Union. And also, like I mentioned, this is kind of optional because you'll be able to pull down my own model that I'm going to train. But if you want to train your own model and save it to your own version of Hugging Face Hub, then you'll want to have a Hugging Face account. It's free to sign up. It should be very quick. You can use Google as a single sign-on. And then I think you just have to verify your email, and then you should be good to go. So I'll give everyone a minute to kind of get set up here. Again, go to that Open in Colab, save a copy in Drive, sign up for Union. Once your sign up does go through, and like I mentioned, let me know in the chat if you signed up and you're not seeing anything. I can see if I can go ahead and push you through. Once you are signed up, you should be able to go to this other link, which is serverless.union.ai, and you should see some form of dashboard there. My dashboard will look a little different than yours because I've been running workflows in here, so yours will actually be empty, but you can see these are kind of the workflows I ran in the last 24 hours. I can go look it back a little further, and we're actually going to build this workflow. This is where we have that download data set, download model, train a model, and then verify data and annotations, evaluate the model, and then upload the model to Hugging Face Hub. You can embed visualizations directly into each task node too, which is pretty cool. So I'll talk about this when we build it. But every time I train a model or load in data, I always like to verify it and read it in because I've had instances in the past where I read in a data set and I was very sure I read in the annotations correctly, but then my model wasn't learning anything. And then I looked back and I made a mistake reading in the data and the squares were all squished or in a wrong order. So I always like to verify that when I read in data and annotations that they look correct. All right, so chat has been quiet. Did anyone make a copy of this notebook that wanted to? Were you able to sign up for Union? Be cool if at least one person says, everything looks good, you're ready to go. Again, I'll give everyone a minute here. And if everyone's really quiet and doesn't say anything in the chat, then I'll keep going. But hopefully, someone said done signing up. Awesome. Great. Perfect. Thank you so much. Like I was saying, at least need one person to let me know you're following along, and it worked. All right, so we can go ahead and move down the code. Again, let me know if you have questions as we go. All right, so once you signed up there and we ran this first install cell, you can run this next code cell. And this is just going to authenticate our instance here, or our host notebook, with Union. So now that you have a Union account, you can run Union, create login, serverless, and then authenticate this device. Click this link that gets generated. Hit next. And boom, now you should be logged in to serverless if you got this login successful. So again, we're using serverless, which is technically in beta. We have a version called BYOC, Bring Your Own Cloud, that people have been using for quite some time in production. So serverless, let me know if there's some sort of bug or issue you see. Potentially there could be. Let us know in the Slack, or if you have feedback on that too. So serverless, we have our own cluster that you're just going to be running on. There's GPUs accessible in there. So we'll use a GPU today, but there's actually A100s in there too. So if you want to train a larger model, you can do that. And then bring your own cloud. You can bring your own AWS account or Azure account or Google Cloud, and then run this layer on top of your cluster. All right, so let's build our first workflow. So before we build our more complex workflow that we saw earlier, let's build the simplest workflow I can kind of think of. So we're going to have one task and run that task in a workflow. So every single node in here is a task. That's like you want something to happen in your workflow. And then you're tying these tasks usually together. Like we have that download data set, train a model, right? That would be kind of two things commonly happening in a workflow. And the workflow is the way you tie those tasks in the flow of data together. So here, let's build a very simple one. We're going to import task and workflow from FlyteKit. So I'd mentioned Union's built on top of Flyte. So you'll see this in the SDK here. So we're importing task and workflow. And then we're going to create a function here called hello world. It's going to take a string. We forced typing here. So we say that name that it's coming in is a string. And then also this function is going to return a string. And then our workflow ties it together, which our workflow here is just really calling that one function. But we'll, again, see down below, we'll build a much more complex ML workflow. So let's run this. And then we can run it locally. So we're going to say union run simple workflow.py main. So that's the name of this workflow. And then we're going to pass in a string. It's just going to say Flyte. Oh, and something I should mention here is we use this magic function right now in the notebook where we say write file. It's creating a simple workflow.py file. So now that file actually exists in here, this Python file. And then we're going to run it in a code cell as like a terminal command. We actually just released in the latest version of FlyteKit, and I should update this example to reflect it, a way where you can actually register workflows and tasks directly in a Python cell without having to create that .py file. So actually, you'll be able to kick off these like production grade workflows directly in a notebook now, which is pretty cool. So here we ran it locally. It just says hello Flyte. Now let's run it remotely on the cluster that's managed by Union. So it says running execution on remote should give you this URL. You can click on it, and then you'll get this kind of project view here. And then you can view all the nodes here. I kind of like this graph view, especially if you have a smaller workflow where you can easily see all these. And we can see that it just finished running. It was running. Now it's done running. You can click onto it, and then you can see the inputs from this tab, the outputs, which is hello Flyte here, and some of the information about the tasks and execution. If we want to rerun it, we can rerun the specific task, or we can rerun the whole workflow directly from the UI. So we only have one parameter here, which is this string that we can pass in. So I'll say hello workshop attendees. Let's make it plural. And then I'll just hit launch again. And so in this case, we're just changing a string. But in ML workflows or data workflows, it's pretty common that you might have parameters that you want to tweak over and over again for experimentation. So you can see how this could be really powerful for retraining, like doing a training workflow and experimentation. You could actually just kick off from the UI. You can also kick this off again from your terminal or from the Python API, and just pass in different values to these parameters. So it could be different model types. It could be hyperparameters for those models. And then every time you run this, you get a version of this workflow. So you could actually go back and look at previous runs, look at what the output was. And so the whole version's like snapshotted every time, which is pretty cool. So that's our super simple workflow. And then we'll go build our more complex one down here. But first, just want to mention, if you kind of forget like what parameters you need to pass in, you can add this little help tag. It says name is required. There's a whole bunch of other stuff you can do with running these workflows as well. And I should also mention, like, today we're just going to run this workflow by kicking it off with a run. But you can actually do scheduling as well. It's like built into Flyte and Union. So you can schedule workflows to run at certain increments, like every 24 hours, or you can use something called a sensor. So if like a file changes somewhere and you know there's new data there, you could take that data and then train a model, have that kind of automated versus manually kicking things off like we're going to do today. So again, for the next part, we're going to actually build that more complex workflow. So we're going to have fine-tune fast RCNN model for object detection. Again, it's going to download the data set, download the model, train the model, evaluate the model, save the model to Hugging Face Hub. If you want to do the save to Hugging Face Hub, this is where you need the Hugging Face account. If you don't have it, don't worry. It'll just fail uploading, but you'll still be able to run the part with the model because you'll be able to pull down my model. It's not hidden behind an API key or anything. So this is kind of optional here. You'll want to create a Hugging Face secret called HF token. So you can run this code cell. It'll give you a little text box. It's hard to see, at least in dark mode. You can click on this and pass in a value here. So Union can also manage your secrets for other platforms. And this allows us to connect to other platforms and tools very easily. So I'm going to go to my Hugging Face account. So if you have one, you can click this little icon here and then go to settings or directly click access tokens. I'm going to go to settings, click access tokens. Oops, I guess I have to log in here. Hang on 1 second. Let me log in. But I thought I logged in with Google. Hang on 1 second. Let me re-log into my Hugging Face. I was just in there, so I'm not sure why I got logged out. All right, I'm logged in. So again, go to access tokens. I'll create a new one, workshop example. I'll give it a date. And the only thing I need to allow is this write access. So that gives us a ability to write a model to the hub here. It's going to click check read access by default as well. And I'll hit create token. Now I have this token. I would copy that over and paste it into here. I'm already have a token. So I'm actually just going to stop this here. And I can look at what tokens exist for me. Yours should just have that Hugging Face token if this is your first time using Union. But you can see I have a few other ones in there that I could access as well. If you ever want to delete a token, you can just run union delete and then secret token name. All right, so the next part has a lot of code here. Before I walk through all this code, what I want you to do, because it could take several minutes to train our model, like maybe around 10 minutes or so. So I want to go ahead and get us kicked off training the model. And also for you, since it's your first time running this in Union probably, it also has to build a container image. And I'll show you how it knows what packages to put in that container image here in a second. But first, I really just want you to run this code cell, and it's going to kick off building a container image for you. But if you did create your own Hugging Face repo, you'll just want to change this your username with your username of the Hugging Face repo. So mine is Sage Codes, for example. And I'm gonna go ahead and run this. And oh, it didn't run yet because I didn't run the previous code cell, which created that Python file. Now I should run this. So if you're running this, run this big code cell, and then run this code cell under it. And then I'm going to walk through that code cell here in a minute. And I think there's a couple questions in chat, so I'm going to try to catch up on that as well. So again, if you create a Hugging Face account, just update this with your username. You can see for me, it says an image was already found with the package requirements needed. So it's skipping building. If I scroll all the way up to the top of this file or near the top, right after we import the libraries we're going to use, I have this thing called image spec, which is a feature of Flyte and Union, where we can define really any specifications that we want around our container image. In this case, we're just passing in specific Python files, or sorry, Python packages that we want to download. But you can have other like Linux environment configurations. You can install different things with apt-get. You can install specific versions of CUDA. But for our use case today, we're just going to install these specific Python packages. And then also just want to note for this workshop, everything's kind of in one code cell here. But you can break this up into more modular Python projects. So like, for example, you might have a folder called tasks, and then you might have all your data tasks and evaluation tasks and training tasks broken up into different Python files. So it allows you to write really clean code locally and then kick off those production jobs. Just for this workshop, I'm showing it in one code cell here. That maybe makes it a little easier to follow along. I'm not quite sure. I might change the workshop up later to have it broken out in those modules. So we defined our image here, and then in every task, we are using the same image, but it basically says, does this image exist? Yes, no. If it doesn't, then I'm going to go ahead and build it, which is what's happening for you if you're running this already. I see someone said the serverless wasn't working for them. It's saying you are not allowed to access this app. It sounds like you weren't able to sign up. So, or you didn't sign up yet. Did you already fill out the sign up form? And then it might take like 5 minutes, maybe 6 minutes before you should get an authentication email or like a verification email. And then if that doesn't go through, if you could maybe let me know your GitHub handle, I can go see if I can push you through. So one thing is if you have a very new GitHub account, it might get flagged right now and not get automatically approved. All right, I'm going to keep going on this code though, and I'm going to go maybe kind of high level on some of it. But if you have questions, you want me to come back to it later, we can as well. But just for the sake of time, I think we should be able to get through most of this pretty quickly. So first, I have a couple of helper functions. One is converting images to base64, so we can actually embed our embed images. Oops. Kind of like I showed before in this workflow, if we want to embed any graphics, including like charts or anything we make, we convert them to base64, and you can embed any HTML or Markdown kind of into each task like this, which is nice. Then we build a dataset data loader, which just reads in the dataset that we annotated. So it's going to look at the file path that we give it, and then read in. There's going to be a JSON file that contains basically the coordinates of those squares that we drew in Label Studio. And then we get to our first task, which is that download data. So I showed a little bit of this before. To make it a task, you add this decorator above the Python function and then pass in parameters here. So we say the container image we want this task to run on is equal to image. That's the thing we defined up here. So once our image is built, it's going to go ahead, pull that, and then run our task on that image. Here we're enabling something called deck as well, which actually I don't think I ended up using this, but that enabling in deck is this is called a deck. So it's like called a Flyte deck where you can embed that HTML or Markdown in any visualization in here. So to get this on a task, you enable deck. And then this one I do want to cache. So if I rerun this workflow, it's not going to download the data set again unless I give it a new cache number. And then we also request the specific infrastructure that we want this task to run on, which in this case is 2 CPUs and 2 gigabytes of memory. We'll see how to access a GPU later. But again, this makes it really easy as an AI engineer or ML engineer for me to just run all my tasks and just declare the compute right here. I don't have to go through anyone to get my model or tasks running on any specific compute. And then this is our actual task here, which is the download HF dataset. So I hosted my data set that I labeled in Label Studio on Hugging Face. So by default, it's just going to pass in these the URL for it, but you could pass in your own username and your own URL for your repo if you made your own data set later. And then it's going to output something called a Flyte directory. And Flyte directory is a directory in the Flyte format. So if you've never worked with containers before, every time we run one of these tasks, it spins up a container. And then to get data into another task, it's also a separate container. So it doesn't just inherently have access to the data that existed in the other container. So you have to specifically pass files between them. And that's what we're doing with Flyte directory. It serializes that directory and deserializes it. And then you can have access to the output after this container spins down. And then we're really just downloading that data set, nothing really fancy going on in this task. And then we're visualizing that data. So this one, we're actually using that deck, same container image, basically same level of compute. Or maybe it was a little more because we're actually doing something with that data here. So we're getting that data set that we downloaded in the other task. And then we're really just using matplotlib to plot out that image that I've already shown you a couple times. So I read in the annotations, I read in the data, and then I put those annotations on my data set to verify that it looks like they're read in correctly. Again, very important thing that I always like to do every time I read in my data set. Yeah, so you just make this into any HTML. So you can embed like Python variables in HTML here, and then add that into a deck, and then have those visualizations there. Then we have our download model. So we're just using a pre-trained model from PyTorch, and then we're going to be fine-tuning it on the classification task. So we are getting this faster RCNN model with a MobileNet backend. There's different backends that you can have. Faster RCNN is like the object detection part, and then there's a classification part. MobileNet is a small enough model where you can run it on a Raspberry Pi or on your local computer, like we had mentioned before. So that's what we're using today. But you could use a larger backend, like ResNet is a popular one. It probably wouldn't run on a Raspberry Pi, or it might even struggle on your local machine, depending on what CPU or if you have a GPU. And but it might be more accurate. So you want to play around sometimes with selecting different models. And we're going to download the pre-trained weights for it. And then we have our train model task. And now we're requesting a GPU in our infrastructure. And we're going to pull in that model that we downloaded above and the data set that we downloaded to train on. And then we pass in the number of classes. I should add this in here where it's just number of classes plus 1. But for this specific model, it takes in like the number of classes you want to predict plus 1 as a background class. So sometimes, again, you want to read the documentation for your model, especially if you're just importing it from something like PyTorch, where you might have to add in some stuff like this, like, oh, like it's number of classes plus 1. We're doing 2 classes today, so this number is equal to 3 is what we pass in. I should just make it a variable here, though, so it could be less confusing. The number of epochs is how many times it's going to look at the full data set and learn from it. So when we ran it, it was going to be 20. And the mean best IOU. So IOU is intersection over union. So instead of just having an accuracy score like classification models do, you actually get a score around how well like these bounding boxes are drawn around the object. And it knows that from like your data set that you made. So it can actually see, like, instead of just yes or no, was this classified, you want to see how much the bounding boxes match up to each other in the evaluation data set. We have to run it on CUDA, which just means we're going to be running it on a GPU here. We get our data set again. We load in that data set with our data loader that we had defined. And then inside our features, so because we're using a pre-trained model, I think it has like 90 classes or something like that in there. And what we want to do is we basically chop off that last layer of the neural network and then put in our number of classes, which is 3 in this case, or 2 plus 1 equals 3. And then we have some other stuff around optimizing. I won't go too deep into this. Again, I'm going to go high level here to make sure we get all through all the code. I can come back later if people have questions or you have access to this. You can dig into it or ask, copy it into ChatGPT and ask some questions about it there. We have a function that's basically just going to look for badly labeled data as well and filter those out. So sometimes if you're taking a data set from somewhere, it might have some weird stuff in there. It kind of looks for that, like do bounding boxes not match up? If not, then get rid of them. And then we have this evaluate model. This is where we compute the IOU and accuracy. Basically, it looks like a lot going on here. It's just because we have to read in all that data in the JSON file that is telling us where those squares are and then how well they were predicted. We get our training loop. So for each number in the number of epochs that we give it to it, it's going to basically read in that data and learn from it. And then we have our evaluate task, which is we have our train model now. We're going to read in our data set again. One thing I'll mention here is you'll actually see on here, I kind of cheated. I used the same data set to make predictions on. You should have a larger data set. I didn't have time to make a larger one right now. So I was reusing the training one. So we're cheating here a little bit. Our accuracy will probably say it's pretty high because it should be. It's looking at the same data set. But you should, when you create your own, have several extra images and put them into a separate evaluation data set. And then we're going to basically plot those out. So actually, if I open up that task here, if I look at my evaluate model, I'll have a flight deck as well. And this isn't just reading in the annotation. So this is now plotting the model predictions on here. So we get this little square and it says what class it thinks it belongs to, either 1 or 2. And then also the kind of confidence score that it has. So it's like 99% sure. It's a union sticker here. And then this is a flight sticker if you didn't know what the symbol was, the open source symbol. So you can see the confidence level and the class predicted now in there. And then you also get a score here. What was the mean IOU? So again, if this is 1, it would be perfect. They're not perfectly aligned. They look very well aligned, but they're obviously probably slightly different than our annotations. And then you have your accuracy. In this case, none of them were mispredicted into different classes or not predicted. So our classification accuracy is actually 0, 100%. But our writing, like the bounding box over it, might be slightly off. And so, for example, this one, you can see my annotation probably was a little bit tighter on this. So this bounding box isn't perfectly aligned, probably with where it was, but it's pretty well aligned. And again, we're using a small data set today and only looking at our data set 20 times. Usually you'd have much more data and more training time. So this is actually pretty good looking for what we did today. So that's what this evaluation data set or evaluation step is doing. Again, it looks like a lot of code. Don't get too worried about it. And then a lot of it's also making that report, that kind of report that we just looked at. And then we upload our model to the Hugging Face Hub. So again, it's another task here with that task decorator and then requesting resources. And then the only thing different in this one that we haven't seen yet is passing in the secret. So we created that Hugging Face token secret that gets passed into this task. And we have our function, upload model to hub, takes in a model and a repo name, and then uploads it. So we save the model into this task. And then we're basically, if you're running this locally, it looks for a token locally. If not, then it looks for that union secret. And then on the Hugging Face API, we're saying if it exists already, that's okay. You can read right over it, getting the token, the Hugging Face repo name that we created. And then we're calling this upload file. So this is the file that we're looking for locally. And then this is what it's going to be called in our repository when it's uploaded. It's PyTorch model bin. And then repo name, the name of the repo that we're writing it to. And then you can add a commit message here. We're just saying upload faster RCNN model and then pass in that Hugging Face token. And then we're going to tie that all together in the workflow. So remember, the tasks are those kind of individual steps that we saw in the workflow. And the workflow is how those tasks tie together, how the data flows through them. So we create a dataset directory that comes out of that download dataset. This actually gets cached as well. So if we reran the workflow from the UI, it actually won't download the dataset again until we tell it to. And then same with the model as well. And then we have our verify data and annotation tasks, takes in the data set, plots out the annotations like we saw. Our training model, which takes in the model we downloaded, the training data set we downloaded, the number of epochs and the number of classes, and then the evaluate model, and then the upload model to hub. And so if you ran this, if I go back, I think my newer execution should be done by now. So they're all green, means yes. And this is the one I just ran. So if you actually were following along and you put in the Hugging Face token, all these should probably be green for you now as well. And we can see that it took 10 minutes to train our model. So when it looked at our data 20 times, spinning everything up, it took about 10 minutes in this case. And I think I already kind of showed, just as I was building it, kind of all the interesting things in these tasks. It's like evaluate model. Again, that's a cool thing to look at. If you just train this yourself, you can pull this up and be like, I made a computer vision model, and this is how it's performing on the data set I passed in. But now that we have this model, we should also have it uploaded to our Hugging Face account. And so if you didn't do this part, you'll be able to pull down my model in the next part. But you can see I have this model here. It was updated 5 minutes ago for me. And I can just see that inside here, that PyTorch.bin model lives in here now, and then I can pull it down. So if I go back to my Colab notebook, we built this whole production grade workflow. Again, if I wanted to rerun the whole workflow, I can hit this relaunch, pass in different parameters here. So I only have a couple hyperparameters like the number of epochs and classes here, but you could add in the other optimization stuff here too. So again, if you're experimenting a lot, it's really cool to parameterize all those stuff in your tasks and then just be able to relaunch this from the launch form. No problem. You could even set different repos here if you wanted to as well. Although everything's versioned in the Hugging Face repo as well. So it's kind of like doing a git commit there. But then you also have a version of your whole data lineage and whole pipeline now every time you rerun this, which is very nice. So if I go back to my Colab notebook, and also, I think I'd mentioned this before, but like relaunching everything here, getting data, doing all that, you can do it from the UI like we've seen so far, but you can also do all that from Python API. It's really easy. You just initialize a remote instance with Union, and then you can kind of pull down data, relaunch forms, pull down model artifacts and stuff like that. But for this workshop, we're going to download the model into our Colab instance here. So you could do this on your own laptop as well, or like I mentioned, on a Raspberry Pi, and actually I have code down below that kind of shows how to run this on a webcam that I won't be able to run during this workshop, but you could take the code and run it on a Pi or on some other device. So let's go ahead and do some imports here for the libraries we're using again. And then also just noting, so in this instance, like if you use Google Colab before, they give you free access to some GPUs, but we're not going to use it today. Everything we're going to do here is using just CPU. So we're going to use our model now on a CPU just to kind of show like you could do this on your own laptop or with a Raspberry Pi as well. So here is my repo ID where my model is saved. If you have your own Hugging Face ID that you created, you should update this to your username, and then you actually pull down your own model. If you don't update this, it's fine. It will just pull down my model, which should work for you as well. And then we are creating our model file from the file we download. We're initializing the model like we did before, and we're also, again, kind of removing that last layer of our model and then putting in the classification head for the number of classes we want to predict. So let's go ahead and run this. It's asking me for secret access. I can hit grant access or cancel because my model doesn't actually need an API token for you to download. And this is what the actual model looks like. If you've never seen a convolutional neural network before, I won't go through all this, but this is all the layers in that network, that deep learning neural network that we built. And this is actually the last layer where we lopped off the pre-trained values, put in our own, which you can see the output features here is 3, because again, that's the number of classes plus 1 that we're trying to predict. And then we can go to our next cell. Let's download the data set that I had created before as well, so we can run some inference on it and on a video. So this just contains the images that we trained on, but we can also use those to kind of see how our model performs. And there's a video in here. So we actually take this model and run it on each frame of video, stitch them back together, and you'll get that cool looking video that we saw at the beginning. So again, hopefully you could go to Label Studio, build your own data set, and then build a really cool computer vision video that you can share. And people love looking at computer vision stuff. We can see labels. 1 is union sticker, 2 is Flyte sticker. We just created a little label map there. Again, we're going to run on CUDA if it exists, but again, we're just using a CPU today. We're loading in a font to make our annotations look prettier. So basically before, well, let's just run this so you can see what it looks like. Before we were just like drawing a simple rectangle around our image, but here is, we're putting way more colors into it, and you can customize this. So like if you want to have classes that are completely different colors or transparency and stuff, you can get as fancy as you want with this. And then we're just looking for, in that JSON file, each box label a score, and then drawing the label around it. So you'll see what this looks like here in a minute. One thing to note is this score value. You'll want to adjust this threshold as needed. So we're just saying draw the rectangle if you're like 60% sure it's that object. Otherwise, don't. If this is a really low value with some models like the one we're using, you'll see it'll draw rectangles all over the place. So you want to find that threshold of what's a good prediction value for it. So now this should have saved our image. And if you explore our files with this little folder icon, we see we have this output image.jpg. You can double click on it. And we can see that we actually get this much prettier annotation than what we had before, which was just those hard rectangle lines around the objects. So now we have this nice transparent whole green box around it and a blue transparent blue box around this one. But now let's put these together and make this look really cool in a video. So you can go ahead and run this code cell. Takes a few minutes to run just on the CPU. So again, using CPU here, not using a GPU because our model is actually pretty efficient. And label map again, we're doing everything kind of like we did above, where we are basically looping through every frame of a video though, and drawing those rectangles. So the difference parts is we're setting up this CV2 video capture. CV2 is an OpenCV, which has a lot of features for like loading in videos and images and doing processing on them. So we're getting like the width and height from that. And then we are basically just writing out to a file called out.mp4. You can pass in all these other like codec parameters and stuff for it. But again, we're just looping through each frame of the video, drawing the boxes kind of like we did above. In fact, we're using the same colors and everything as well. So we're not defining all those down here again because they kind of exist above. So if you wanted to, you can play around with these colors and color fills. So the color fill is that transparent color that we saw kind of throughout the whole rectangle. And then these are the same colors right now, but if you wanted to have the border of the rectangle a different color, you can mess with this. I guess these actually are less transparent. So we should be able to see a rectangle and then more transparency inside that rectangle. And this should just take, oh, I think it's already done. I thought it would take a little bit longer. So already, now I have this out.mp4 and I can double click on it and should download. And if I click on my download file, we now have this video that I can click play on. And it's doing pretty good. I think for us, we might have wanted to adjust that threshold a little higher in this case. We can see that sometimes it puts like a double box there. You can see that it's not as confident there. It's only 65% versus this larger one is 95. So maybe we would adjust this parameter to be a little bit higher value. You wouldn't get that double box, but at the same time, we can see this one is not predicting on that anymore, but it did earlier. It just doesn't have a lot of examples in the data set of like a partial sticker, probably. Also, we don't probably have any in the data set maybe orientated in that fashion. So one thing we didn't do that is very common in a lot of computer vision projects is something called image augmentation or data augmentation, where you could read in our data set and then flip it and do skews to it different ways. We didn't do that in our case. So I think all the stickers were basically laying that way that we're seeing down here and has a pretty high confidence score on it. But when it sees it sideways, it has a much less confidence score on it. So we want variations of our data set that we know are going to appear. We want as many variations that we can. So that might be different angles, different colors, different sizes, or like the camera being zoomed out if we know that that's going to be something our model encounters. And if you were able to follow along with all that, I know we went through a ton. So if this is your first time doing like computer vision or deep learning, some of this might feel like a little out of depth for you. That's okay. You can come back again, look at the code, ask questions later as well if you want. But you were able to go through and actually train a computer vision model that is a pretty common one, the faster CNN. It works really well. You're able to run it on a CPU device. So again, you could run this on something like Raspberry Pi. And in fact, this code down here doesn't work in Colab because it needs access to your webcam. But you could look at how I did this for like my laptop or for running on a Raspberry Pi. Very similar to like we did above with the images, but instead you're capturing a live feed from whatever port. So like by default on a Raspberry Pi, I think 0 is where the camera lives, but you might need to change this number. If you plug in a USB camera, it might be on a different number here. And basically, we're just going to read in each frame and then draw out the predictions like we did for the images and videos that you just saw. At the bottom here, there's more resources for you to go learn as well. Learn more about Union, check out the documentation, go look at Hugging Face, more on PyTorch models. Actually, a fun challenge for you if you liked this and want to do something else is do this, but with a slightly different PyTorch model. So different object detection model. Label Studio, go check them out. And again, they might be one of the easier ones to just kind of get started with building your own data set. And then for me, I uploaded that data set to Hugging Face Hub, and then I pulled it in. But if you're developing this project locally, you could also read from a data set locally if you wanted as well. All right, what did people think? Were you able to build a computer vision model? And not only a computer vision model, but a robust pipeline that is, maybe pretty similar to stuff you'd actually build in production as like an MLOps engineer or a computer vision engineer putting stuff in production. Had anyone ever done anything like that before? And if not, what'd you think? Was it kind of easier than you were thinking? Was it harder? After people had said it worked earlier, I still see there's quite a few people here, but the chat's been quiet. So hopefully people didn't get stuck. If you did, you didn't put in the chat, so I didn't know. And I know we went through stuff pretty fast here again. Like if you're newer to machine learning or PyTorch, this could seem like a lot. And then again, that's totally fine. At least like one way I like to learn is kind of jump in and start using stuff and then going back and like looking at the code and learning more about it. If you thought this was interesting, definitely stay in touch somewhere on LinkedIn or in Slack. I'll be doing more workshops in 2025. So this is the last one of this year before the new year. And I'm really excited to redo some of these too. And like I mentioned, I think I'm going to redo some of these with the projects broken out more, probably how you would actually write this in production if you're doing this for like a real MLOps project. Makes it a little bit cleaner to read. Again, you can go look at like your training code. This is my training task here. This is just scikit-learn, so it looks a lot simpler than what we saw today. We could break them out into these modules, which is pretty cool, and then import them into your workflows. We'll also use artifact management, which is a feature I kind of mentioned, but it makes it really easy to manage like model versions and data versions across your whole pipeline and hand those off between teams. It's also pretty commonly like the workflow we saw today. You might actually do something like this. It just depends on your team setup, but it's also pretty common that you might have part of this done by like a data engineering team and another part done by an ML engineering or MLOps team. So like the downloading data and downloading model, like maybe this is done by some other team where you're not just downloading a data set, you're actually doing like pre-processing and saving saving a data set in a certain state. This could also be something like a vector database if you're doing LLMs. And then you want to be able to pass off that specific version and have the artifact version, and then pass off those different versions to different teams. And then you might read in this artifact to a separate workflow. So you might have like a data set workflow or a data engineering workflow, and then you might have an ML engineering, ML training workflow. How do you communicate between those teams easily? Artifacts really helps with that. Also, one thing I didn't mention is we also have cost use this for cost, but basically utilization tracked for the task. So in this case, we over declared. We said we wanted 8 gigabytes of memory, but we actually only ever used just above 2. So we could have said 3. In this case, it's not very expensive for us, but it could add up over time. But also, I might have declared, instead of 8, maybe I declared like thousands of gigabytes or 100 gigabytes or something, and I was way over declaring what I was actually utilizing. So you can actually see this and then pull it down into the right amount, and that can help save you a ton of money in your workflows as well. And if you're on the Bring Your Own Cloud version, we're rolling out a larger org cost observability type of thing that you can check out as well. If you want a demo of it, you can get a demo, and then we can see that we used our GPU for 7 minutes for our 10-minute time in this container. Actually, yeah, I'll go to Union, and if you want to see some of these newer features, so there's still people here listening. I wrote a blog a couple weeks ago, came out during reInvent, and it talks about some of the new stuff we have coming out. So 1, the cost observability dashboard, like I kind of mentioned. 2, this is actually out in serverless right now too. It's something called Actors. So it gives you a long running stateful container. So right now in our workflow for training purposes, we just spun a container up here, and then when it's done, it spins back down. But actually in our workflow, we reuse the same container image across all of these. So if we wanted to speed up our workflow a little bit, we actually could use something called Actors. You can also use this to serve models. And what this does is it gives your container a time to life. So it doesn't spin up every time, and you could reuse that across all those tasks. So we could say, spin up this container and then stay up for 5 minutes when it's not being used. So if it's still being used, it'll reset that time. So you could reuse it as a container for every single one of those tasks, and it wouldn't have to spin up a new one each time. So it can actually save you a ton of cold start time if you have a really complex pipeline and you're spinning up images all the time. You can also use it to host stuff. So it gives kind of a near real time or a faster batch inference. So you could have a model hosted in that container, and then when you ping it data, you can get predictions back. But you can have this model kind of live indefinitely until you spin it down. And then also we're launching serving in the next couple of months. So if you want to deploy a model kind of just within the whole Union system, make it really easy to go from your workflows and artifacts like we had talked about to using that in production or having it deployed somewhere where people can actually interact with it. It's just going to be like another call from your terminal, and you can build an app with like Radio, Flask, Streamlit, really whatever you want. You let an API endpoint and then have your model accessible really within like, I think a couple minutes or even less of it, which is really cool. So I'm excited to show this off in the new year. We'll be incorporating all these into some of their workshops, and you'll be able to see how to do like full end-to-end ML and computer vision, and I'll also be doing stuff with large language models. If you want to check that out, again, like I was saying, stay connected on LinkedIn or in Slack is probably the best place. I'll share those links again here. Slack channel. If you have questions about anything that we covered later too, ping in there. And then let me grab my LinkedIn and I'll share in the chat one more time too. With that though, that's kind of the end of the workshop. Again, chat's been a little quiet, so let me know what you thought. Otherwise, I'll wrap up the stream and hopefully I will talk to some of you all later though. Someone said, thank you so much. No problem, my pleasure. Always really fun. Again, if you have feedback on platform, let us know. I always love hearing like what you thought about it, especially if you go through and maybe make your own model or try to make your own pipeline that is a little different than the one I just showed you. Always really good to get feedback on like what it actually felt like developing with it. And again, you should try annotating your own data set and making your own model. Someone said, thank you. Absolutely. Hopefully you were able to follow along. Again, no one said that they got stuck, which is usually a good sign because usually when people get stuck, they do put it in chat. No one said they did, but no one said they also completed the whole thing, even though it sounds like you were able to get the first workflows to run. So if you did have any trouble, feel free to ping me later as well. With that, though, I will wrap up the stream here. Again, thank you, everyone, for coming out, and I will talk to you all later. Look out for a lot more cool workshops and content in the new year.